So for this question, we're going to try and find the steady state error for 3 different inputs. You'll notice that this one corresponds to a step input, this one corresponds to a ramp input, and this one corresponds to a parabolic input. And we need to first ensure that the system is stable because our steady state error equations don't really make sense if you don't have a stable system. So let's start with that. So to assess our stability, what we need is the closed loop transfer function, or the overall transfer function. And that's when we consider the feedback in here. So we need to figure out our closed loop. If we figure out the open one first though, okay, open is just whatever you have on the top line when you disregard this feedback. So it's just going to be what we had here. Okay, and H is the transfer function for what's in our feedback loop, and we have a unity feedback system because what's at the output is just taken straight back and compared with the input. So H is just equal to 1 in this case. So we can calculate the closed loop, or the overall transfer function, okay, using this equation for negative feedback, substituting in we get that. We have these complex fractions that we need to try and cancel down a little bit, but the trick, if you remember, is that when you have unity feedback, essentially your transfer function in the closed form just ends up being the open transfer function, this one here, with the numerator added on to the denominator as well. So you can either go through and cancel these fractions properly, or you can shortcut it where we get the numerator added on the end as well. So now that we've got our closed loop transfer function, what I'm interested in is our characteristic equation that comes out the bottom, and we need each of the different powers of S. So we're going to need to expand out the brackets here. And if you go ahead and do that, this here all simplifies to just be S squared plus 31S plus 175. So what we can do is either apply our Ruth table at this point to assess whether we have any sign changes in the first column of that table, or because this is such a simple system, it's only a second order one, we can actually just directly solve for the poles. And we can do that using the quadratic formula. I'm just going to spit them out. So if you do that, you end up with poles at negative 23.58 and negative 7.42. So both of these poles are negative, which would suggest if you draw them on your real and imaginary axis, they're going to be sitting over here on the left-hand side of our imaginary axis, which means that this system is stable. Okay, so now that we've proven that, we can go back to the real task, which was to find the steady state error. Okay, so let's go and do that. Alright, so first thing we need to do if we're going to do the error constant method is we need to figure out what the system type is. So system type is assessed off the open transfer function. We need to look at how many integrators are on the bottom line. So that's S's on their own factored out of the equation. So we can see that we have no S's factored out here. So therefore, it's going to be a type 0 system. So now let's look at the first case, which is when R is equal to 2 on S. So this is a step input. Okay, so we can go ahead and look up what our error constant should be for a step input and a type 0 system. So this here is the table for that. So we said that we are a type 0 system, so we're looking at this line, and first one is a step. So we need to calculate this. This is our error constant, Kp, because it's going to appear in here for the steady state error. So Kp, the equation was the limit as S goes to 0 for our open transfer function. All right, subbing in. So the open transfer function we said was this one here. Okay, double check that nothing cancels out. So yeah, we don't have any s's on the top and bottom line that are able to cancel. So we'll sub in our limit now where s is 0. So we're going to get 3. S goes to zeros here, so it's 5. We're going to get 8 and 20. So if you calculate out that number, it gives you the error constant, and it's about 0.09375. So now what we need to do is convert this into our steady state error, and that's given in the table. So again, we're looking at the step 1. It's 1 on 1 plus kp. And this time we're going to need to multiply it by the size of our input. So because our input is a 2 on S rather than a 1 on S, we need to multiply this by 2. So subbing in, and calculating it, we end up with an error of 1.829. Alright, so now let's go back up and have a look at our next input. So the next one that we needed to consider was the ramp one, which is r is equal to 5 on s squared. So this is the ramp. So again, we can have a look at our table. So we've got a type 0 system and a ramp input. So no matter what, it tells us that the steady state error for the ramp input is always going to be infinity. So that's another answer here. We've kind of shortcutted it a bit by looking it up in the table. So the last one they needed to do was the parabolic input, and this is where r is equal to 5 on s cubed. So let's write that down. Sorry, it was 10 on s cubed. Let me fix that up. Alright, so again, if we look it up in the table, we have a type 0 system, parabolic. The error that we see is going to be infinite. So that's our last answer. So I've gone through and actually made a code in MATLAB where I'm able to compare whether my theoretical results match against my simulated results. So if we start by looking at the step input, we decided that the error should be 1.829, sorry. So if I jump over to MATLAB, I've written myself a code to simulate this. So this part is setting up the transfer function. I'm looking at simulating the overall transfer function's response, so that's including the negative feedback, which is what this step here is. I've set up a time vector. This is because I also want to plot the input function so that I'm able to compare the output or the response to that input. And this here is looking at actually plotting stuff for the step input. And we've got a 2 on S for the transfer function. So setting up a figure, this step here is actually plotting the response. So I'm looking at doing it for the overall transfer function, and I need to multiply it by 2 because I have a 2 on S rather than a 1 on S. And I'm plotting it to the end of my time vector, which I set up, which is 10 seconds. This here is setting up my input, and I'm plotting my input, and I've got a legend, so it will show me which one is which. So if we take a look at what it plots, this is it. So the red line is the input, and we said it was a 2 on S, which meant it was an input of 2 when we plot it in time, so that makes sense that it's a straight line. And this here is my response. So here we can see that there's a massive difference between our desired or our input value of 2 and our output or our response value, which is hovering just under 0.2. So if we wanted to, we could actually find out what it was by looking at our steady state value. It puts up a little marker that we just need to click on to find out what it is. So if the final value is 0.17 and this is equal to 2, the difference between them is the steady state error, and that is going to match what we had in our calculations, which was 1.8. Alright, so if we now focus on our ramp and our parabolic inputs, we calculated that we should have infinite steady state error for these two cases. So jumping back to MATLAB, I've set them up as well in my code. So I'm going to simulate the ramp input, remembering it's a 5 on S. So when I put it in for the step response, I've got my overall transfer function. It's multiplied by 5 because it's an input of 5. And then I've divided by S to account for one of the S's in here. The other one is accounted for in the step part. So I hope that makes sense. Same thing for parabolic, it's a 10 on S cubed. So when I go to simulate the actual response, one of the S's from this input is accounted for in the step part. The other two I've put in as part of my transfer function. So when we simulate them, we can have a look at what we get out. So this is the ramp one. Our input is the red one, and that's what our response is supposed to be trying to match. They're supposed to be the same. But you can see that there's a massive difference, and the difference at any point in time is just increasing massively and more and more and more. So that's the sign that it's definitely got an infinite steady state error for this system, which is not good since it's supposed to be a control system. So this here is the last one, which is the parabolic system. So again, the red line is the input, the blue line is the output. So we want these to match, and you can see that at any point in time, we don't have them matching at all. And in fact, the difference between them just keeps increasing and increasing and increasing, which is again a sign that we've got infinite steady state error, which matches our theoretical predictions. So that's all there is for the video, and see you in another one.